Fatima Garcia.
You know the shape. You may remember from grade school that the columns and the rows are important, and you might recall that there were some empty spots towards the end that still needed to be filled. The periodic table of elements has been hanging in classrooms and chemistry labs all over the world for decades. So what would you do if I were to tell you that its classification system may not be totally right? The table arranges the elements based on their proton number. This is how we define them to be elements. And the columns and the rows arrange them based on their electron configurations. And it is these electrons that give elements their chemical properties. For 150 years, the table has allowed us to predict what new elements we're going to do before we even discovered them based on their placements. This, however, started breaking down once we began discovering the super heavy elements. These are those elements above number 103, and they're starting to behave in some really strange ways. Oganesson, for example, element 118, and one of the last ones to be officially named, should be the very last noble gas in the group. Theory, though, is predicting that it'll behave more like the elements in the volatile nitrogen group. Copernicium, on the other hand, element 112, and named after Copernicus, is behaving more like that last noble gas. If we follow the numerical ordering, then the chemistry no longer makes any sense. And if we follow the chemistry and the configurations, then things are no longer in order. And this is just one of the many conundrums currently facing the table as it stands, with an international team of scientists trying to figure out what do we do. There's a debate going on. Do we adopt a convention? Maybe the shape itself needs to change. The community has requested for more experiments so that we can find a way forward. However, you can't just take these guys off of the shelf to then get it on the benchtop. First, you have to make them. This is difficult. Usually, we can only make them at the rate of 1 out of a week or 1 out of a month. Then you have to watch the chemistry. But these guys are radioactive, so they will decay away. So you have to do your measurements fast enough. This is exactly what we do in the heavy elements group at Berkeley Lab. We do modern-day alchemy. We take a beam of ions and hit it against a stationary target, making our new heavy element. Once it's made, we can trap it using a series of electric fields, and into this trap, we can inject a series of gases to do chemistry. We can see what the element reacts with and what it doesn't, giving us information about its chemical properties. At the rate of 1 atom a week or 1 out of a month, it'll take us a while, but our experiments will provide the community with the key information needed to settle the great periodic table debate. Maybe one day in the future, the periodic table of elements won't look like a table anymore, and chemistry itself may not be as it was once.